So, 5 days left to of the 28 days that I am out data structures in binary trees, and we're looking at tree traversals. This website I've used for many years. It's out of Singapore, and it just helps to walk you through how these algorithms work. And I kind of get it, but I kind of don't get it right now. Like, I feel like it's just, I always review the content, I never have to do it over a long period of time. So, we're going to go through this and probably some other stuff because I really want to get this down so that I can go to the medium level uh, stack implementations because I'm learning how to use stacks. Actually writing a lot of code to be more software engineering like versus, oh, this is good to know, I get it. I might need it later on in data science sometime. So that's what we're doing. That's what we're here for. And it is basically a specialized type of binary tree vertex, right? And how it looks at it. This will walk you through how to do everything, but here you have that, and what we're going to do is I'm going to have them walk through it a little faster. It normally highlights the, hold on, search. There we go. And it's going to walk through the code here until you find what it was looking for. And so I want it to get to, let's get it to 61. So it starts here and it goes to the right. It starts with checking if it's null, returning if it's this, and if not, it goes to the right, and then it goes to the left. So this goes to the right, and then it goes to the left. I wonder, like, how does it know? Hold on. Let's go back to search. That's really on. I wonder, how does it know, like, which side is which and why? So it can't know that you need to go there first. I guess it depends on how this tree was made. Because there's something. Because I don't believe you just know 8's there. And you can switch between e-lecture mode. It's a good tool. So it's going to just traverse everything. For traversals, it goes left. Okay, here. So for traversing the root, which is what we're doing, it has the visitation sequence, which is what we're getting out of ordering. So first we check if it's null, then we go left, then we go right. So for traversal, you go left and then you go right. For pre-order, return what is there first, then go left, then go right. And then it goes back because it's null and it needs to go to visualizing. Honestly, part of me is so tired. I want to just like look at the screen and hope that the information converts to my mind. That seems like the better option. And where'd my code go? Because I already submitted it. I guess it's a good thing to delete it because I don't know what I submitted anymore. Anyway, but it's an in order traversal, so the first thing it said to do was if root is null, return this. So that's step one. So in order traversal, I'm not in order. Go left, then go right. So we're going to have root dot left and then root dot right. And the other thing we're going to need is up here, we're going to need a stack to put everything on. So while stack for I in root for I in root right. I know this is wrong. I'm trying to remember why I need to pop something to a stack and push stuff in off the stacks. Stack dot append stack dot append and there's not been any popping. Stack dot pop. Actually, I might need to pop first. Okay, let's see what this does. Null isn't defined. Oh, hold on. Let's come back to that. Let's check the. So I have one right and nothing else right. So basically it returns null. It's not actually popping and reading anything correctly yet. Okay, let's put some print statements in here and figure this thing out. Let's print root left. Or actually, you know what? I don't think I'm actually getting the value because I'm going left and I'm going right, right? I might need to actually append root value and then just have it go left or have it point right because it's basically a pointer. And it didn't print anything. No standard out. Okay, so let's do this. Root value. So let's go left. Root equal root dot left. So root, because it needs to keep hold of its position in that variable. Okay. And let's print root val. Still not getting any standard out. I hate when I can't see what it's doing because it's just how I taught myself was printing out and making sure it was getting what I wanted. So it's like, how can I know what's wrong if it won't print out? It's really useless terminal. Why won't it print? There's nothing wrong with the print statement. Can I print root by itself? Okay. I can't print root by itself either. Is it because I changed browsers today? So frustrating. Can't pop from empty list. Okay. Okay, so I can't traverse iterate over root. So what did I do yesterday? No idea. Let's watch a video. But I don't want the code. I kind of just, because you can't actually do well replicating if you don't just. Figure out what it's trying to get you to figure out.
Are you driving way less than you used to? Do you have a clean driving record? Are you over 25?
Well, I can't hear anything. Hold on. I need to share screen again. I don't think there's audio.
very solid before we can build on top of them and do other topics. So if you haven't subscribed to the channel, subscribe to the channel and like this video. What we're going to do today is we're going to talk about our fundamental traversals of binary structures, binary tree structures, and we're going to talk about the types of trees. We're just going to go over our very basic concepts so that we have them very sound. So let's go over 3 of the key kinds of trees, or 3 terms we can use to describe a tree. If we have a tree where leaf nodes have no children, or a node has 2 children, it is a full tree. Notice, this is a leaf, it has no children. This is a leaf, it has no children. This is a leaf, it has no children, and that is a leaf, it has no children. But the nodes that do have children have 2 children. They cannot have 1 child, they have to have 2 children. So this tree is full. Every time we decide to have a descendant, we have to have 2 descendants. We can't just have 1. So this node decided, I'm going to have descendants. I need to have 2. This node said, I'll have no descendants. It has no descendants, no children. That is a full tree, and you can tell by what it looks like. So this is a complete binary tree. Complete binary trees are our binary heaps. We make binary heaps complete trees. So what does complete mean? All it means simply is when we fill out the nodes, we go top to bottom, we go left to right. Do you see how we go and fill it out like this? Do you see how we go top to bottom? And do you see how we go from left to right? And if I just put a node right here, just out of the blue, I stuck a node in there, this tree is no longer complete because I just missed putting a node there. So this is a complete binary tree. And then finally, we have our perfect binary tree. So a perfect binary tree is where all the leaves are on the same level and all of the nodes that decide to have descendants have exactly 2 children. A perfect binary tree is both complete and it is also full. You see how the nodes that decided to have children, decided to have descendants, they only can have 2 children. They can't just have 1 child. But the ones that did not decide have no children. And notice how all of the ones that did not decide, what we call leaves, are all on the same level. This is a perfect binary tree. So now that we understand our terminology very soundly, what we need to do is let's look at these traversals. And yes, these are going to be the raw traversals you can do on a tree, but it's very key to understand these traversals so we can adapt them to other problems. If we're very flexible with traversing a binary structure, it becomes much easier to solve problems recursively or iteratively with a stack. So let's look at our traversal now. Okay, so what we're going to do is we're going to do a traversal of this tree. And there are 3 fundamental ways to traverse a binary tree. You can do it other ways, but these are the 3 key ways. There's your pre-order traversal, your in-order traversal, and your post-order traversal. And I don't want you to worry about the part in the word where it says order. I only want you to notice the first part of the word. Notice how it says pre. Notice how it says in. Notice how it says post. That prefix, the prefix to the name of the traversal, tells us when we visit the node we're sitting at. So what I want you to see is in a pre-order traversal, we visit the node, we visit the left subtree, we visit the right subtree. Do you see how it's called pre-order? Do you see how the n is the first visited? Do you see how it's pre, before the left and right? So for in order, think of it as in. So left subtree, visit the node, and then visit the right subtree. So do you see how it's in? Do you see how it's in the middle? That's how you remember in order traversal. And then we have our post order traversal. We go left subtree, we go right subtree, we visit the node. So do you see how it's post? It's after the left and right. So the left and right stay in sequence. Left and right stay in sequence, but the prefix tells us when we visit the node before the subtrees. The subtrees will be left, right, but when do we visit the node? That's what the prefix tells us. So what we're going to do is we'll do a pre-order, we'll do an in-order, and then we'll do a post-order traversal here. So this is what I want you to think about when we're traversing a tree. I'm going to write something that's going to help you. So I want you to think of recursion. Think of recursion as a certain policy we have to execute at each node. Think of the recursion as the tasks we need to do at a node and the state. The state stays on the call stack. This is the key with recursion. So do you see how I just put node left, right? This is our pre-order. We're doing pre-order right now. And what we want to do is we want to execute the policy at each node. So what we do is we start at the 10. I have to do a node visit. I have to do a left subtree visit. I have to do a right subtree visit. So what I'm going to do is I'm going to do the node visit. I'm going to just output 10. And what I'm going to do is I'm going to erase the n. So I'm just familiarizing you with the example that we're walking through. And notice, we don't just have to print a node. We can do any form of work. The whole point is visitation, get our fundamentals down for visiting a node right now. So what we're going to do is we're going to execute our policy at this stack frame. We're going to say, I need to visit my left. So this stack frame says, I need to visit the left subtree. So we're going to circle the left. Okay, so now we recurse, and now we just circle the left, and now we're going to come down, and we'll come to the 7. What is the policy at 7? 7 says, okay, what do I need to do here in my stack frame? So what we see is, we see that 7 has to do a node visitation. So what we're going to do is we're going to visit 7. And notice the next step in 7's policy in the stack frame is to visit the left subtree. So let's do it. So we visit the left subtree. And now what we need to do is we need to do this policy at the stack frame. So do you see how recursion is we're executing the same policy at each node, but it's going to give us the behavior we desire because of the way we're ordering the visitations, right? So what we're going to do is we'll visit the 6. And then we're going to recurse. And then we're going to come to the 1. We're going to visit the 1. And then 1 says, I need to visit my left subtree. We hit a base case, nothing. We come back. 1 says, okay, I finished my left, so I can erase that. I'm done. And then then what is one's policy? What is the policy at this stack frame? What is left for this recursion in this stack frame to finish? And we see all that's left is visit the right subtree. Let's visit the right subtree. And then we see that there's nothing. So we come back, and now 1 has nothing to do. So now we return to our caller. And now 6 says, okay, thank you, left subtree. You're finished now. What is next in 6's stack frame? And I say stack frames, but the thing is, we don't have to use the call stack. We could make our own stack. We can make our own stack, and then we could execute the traversal that way. So it just depends on the traversal and what implementation you want to do. So this says, I need to visit my right. So the 6 visits its right. There's nothing there. So 6 comes back. So now 6 has nothing to do. It returns to its caller 7. In 7's stack frame, in its policy, its stack frame, it says, I visited my left. And now all 7 has to do is visit its right subtree. There's stuff to do over here, so let's do that. So now 8 says, what do I need to do? What does 8 need to do? It needs to visit itself. It needs to visit its own node. And then it needs to go left. We see there's no left. And then 8 says, okay, I need to go right now. So we recurse on the right subtree, and now we're at 9. What is 9's policy? What is 9's job? And I want you to drill this in your brain, because this is how we really understand recursion. This is how we really see that recursion expresses our decisions at each node. It's different for each node. Each node has a different state. Do you see how states differs? This is a recursion fundamental I want you to internalize. So we see 9. So what we need to do is we need to print 9. We see it has to print itself. And so 9 needs to visit its left, nothing. 9 needs to visit its right, nothing. So it has nothing left. We return to the 8. The 8 finished its right subtree, nothing left. 8 has nothing to do left. And now we come back to 7. 7 was just visiting its right subtree. 7 says, okay, I'm finished. 7 is finished. And now we return to 10. And do you see how this all was the left subtree of 10? Do you see how our next task is to explore the right subtree of 10? So all these traversals do is they change how we traverse this tree. They change when we visit nodes. What we do is we check the right subtree, and then what we need to do is we need to print 11, because 11 has that task to do. And so 11 has to visit its left. There's nothing here, so we come back to 11, and so 11 has to visit its right. And so 11 visits its right, and now 20 comes to itself. And 20 says, what do I need to do here? I need to print myself, go left and right. So 20 will print itself. So 20 now needs to go left. So it comes to 14. 14 needs to print itself. And now 14.
See this property on Zillow? It's a fully furnished property that's been sitting empty for the last 42
14 will go to the left. So 14 finds nothing. It'll go to the right as well. It'll find nothing. And now back to 20. What was 20 just doing? It was looking to its left. So what we're going to do is we're going to finish that. What is the next state in 20's stack frame? Well, we need to go to the right. We come to the right and we see 22. So we see 22, and 22's job, well, it hasn't printed itself. It hasn't gone left, hasn't gone right in each job. So we're going to print 22. And then we'll go left, there's nothing. And then we'll go right, there's nothing. 22 is finished, it returns to 20. And then 20 has explored its right, it'll finish. 20 has nothing left to do, it'll return to 11. 11 has finished its right. So 11 has nothing to do, it's going to return to 10. 10 has finished its right, and 10 stack frame, the top level stack frame that drove us into the recursion, is finished. We're going to return to our caller, whatever we return, whether it's the count of the nodes or something, and that is finished. That is the traversal of the tree. This is what the reorder traversal looks like. The key is you don't really need to memorize these traversals. You literally can get the hints of what they are from the name. Anyway, I think you get the idea now. Let's go through the in order and post order and see how those work out. They're basically the same thing. So now what we're going to do is we're going to do an in order traversal.
It's basically the same. I'm not going to listen to it.
Anyway, we're going to get more familiar.
Still feel like my brain is not computing because I still don't know how to code it. Why is it none? I don't know why I own a pen when it tells me. So frustrating.
Wow, I just built the most amazing workflow on Monday.com.
You build your own workflow? Why?
A binary tree is a common data structure used in software development. It's also a frequent topic in technical coding interviews. In this course, Alvin will explain binary tree algorithms and
So transition, here we are in my text editor. Let's start by creating our node class, right? So you'll be able to follow along in any language that you choose. I'm going to do mine in JavaScript, right? So I think the best way to represent a node is just to use some class. So hopefully you're familiar with some classic class syntax. I'll just create a node class. We're just going to need a quick constructor. And I think it would be valuable to take in the initial value that's going to be stored within the node. So I'll take the in as a constructor argument. I can just set this.val to that value. I also need two more properties. One for my left, so I can say this.left. I'm going to initialize it to null. That means by default, a node will have no left child. The same way, by default, a node will have no right child. Right? So I'm going to use null to represent children that don't exist over here. Awesome. That's all you need to create, a baseline binary tree, right? We're going to use this class a lot during the course to test our algorithms. So how can you create a node and eventually wire up a tree? Well, I'll just call my constructor a few times. I'll create different nodes. I'll just store into some variable names. And I'll, of course, say new node to create a new instance of node. And I'll store some value inside. I'm going to store some characters inside. I'll create a bunch of these different nodes. What we'll want to be sure to do is make sure that you also set their pointers properly. So I'll give each of these some different values, A, B, C, D, during the whiteboard session, right? And this is how you can represent that same tree programmatically, right? So I always think it's valuable to also try to visualize your trees, right? Obviously, we create this tree in a very manual way, probably in the long. Hey programmers, Alvin here. Right now I want to go over this depth first values problem. So this will be a good review of the depth first traversal algorithm. So what do you want to do in this problem? Well, what we want to do is take in a binary tree. And in particular, your function is going to take in the root of the binary tree. And just recall that given the root node of a binary tree, we know that that node is going to have pointers to its left and right children, which may point to other nodes. However, if let's say a node does not have a left or right child, then its pointer is going to be set to null. So that's how we'll represent our binary tree programmatically. But for now, let's just stick to the visual representation of our tree. So for our depth first traversal, we could start with the root node of A. What we'll do is we'll just add that to some collection. And we're going to have to maintain these in a very particular order. And then from there, according to a depth first traversal, I could go to B. And here's where we make our real or remove iteration of this depth first reversal. And now I ask that same question. Is my stack empty? It's not, so I remove the top of my stack decision, right? We can either go to C or D. If I'm doing a depth first reversal, your function is going to take in the root of the binary tree. And just recall that given the root node of a binary tree, we know that that node is going to have pointers to its left and right children, which may point to other nodes. However, if let's say a node does not have a left or right child, then its pointer is going to be set to null. So that's how we'll represent our binary tree programmatically. But for now, let's just stick to the visual representation of our tree. So for a depth first reversal, we could start with the root node of A. What we'll do is we'll just add that to some collection. And we're going to have to maintain these in a very particular order. And then from there, according to a depth first reversal, I could go to B. And here's where we make our really important decision, right? We can either go to C or D. If I'm doing a depth first reversal, I need to go deeper in the tree before I move laterally. So that means I go from B to D. Then once I bottom out at D, there's nowhere deeper I can go from D. And so now I move laterally to the E node. And this pattern continues, right? I don't have anything deeper from E, so now I go to C. And then from C, I go to F. So this would be a depth first reversal on this binary tree. Notice that it goes A, B, D, E, C, F. And again, the really important characteristic is we must go deeper in the tree until we can't anymore, and then we can go across the tree. That being said, how do you actually manage to implement this algorithm? If you're familiar with depth first traditionally, then you know that it's going to use a data structure like a stack. So let's get situated over here. So we'll trace through that again, but this time taking a really close look at how we can use a stack to accomplish that direct order. And so just recall that a stack is a sequential data structure where we can only add things to the top of the stack and remove things from the top of the stack. So a really important characteristic is we can't really insert or remove elements from anywhere but the top of the stack. So when I add things to the stack, I always add to the top like this. When I remove things, it's also from the top like this. All right, so when I begin this depth first traversal algorithm, I'm going to start with the root node of A. And by default, I really just take that root node and I just store it on my stack. So it's the only thing on my stack right now. I'll use these rectangles to represent my different stack frames. And really in my program, that would just mean storing the actual instance of node or some pointer to it. Cool, and then from there.
Okay, let's store my stack.
I actually begin my main algorithm. So the main flow of a depth first reversal will check if the stack is empty. Right now the stack is not empty because I have at least one element. And so what I do is I start by removing or popping the top element of my stack. So I'm going to remove the A, and I'll label that as my current node being explored. And when something leaves the stack, then I can consider it being visited right now. So I need to list out my values because that's the whole point of this problem, right? So by now I've just visited the A node. At this point, I can look at that node's children now. So I look at the A node in the tree, and I see that it has a B child on its left and a C child on its right. And from there, I push or add those two children to my stack. So I'm going to put C first, and I put B afterwards. Okay. And notice if I push my right child first, followed by my left child, that makes it such that my left child is the top of my stack, which means that I would hit them next. And that actually ends on my first iteration of this depth first reversal. And now I ask that same question. Is my stack empty? It's not, so I remove the top of my stack. I'll call B my current, which means I can print it out or insert it into my values list. Nice. From there I consider B's children. B has two children, so I add them both. I push E, followed by pushing D. That ends that iteration. Now something interesting happens. My stack is still not empty, so I know I removed the top, so I call D my current. I add D to my list of values, but if I look at D's children, it actually has no children, right? And so there's nothing to add to the stack from here. And so technically I finish this iteration. And now I still have stuff on my stack, so now I pop E off the top of my stack. Same thing as before, right? I add E to my values. E has no children, so I'm done with that iteration. Finally, I have C. I remove C from the stack, and I print it out in my values. And then at this point, I see that the C node only has one child, so I'm just going to push the children that exist. So I would push the F node.
It's not helping. I think I need a different strategy for learning. Anyway, we'll stop here for today, and I'll see you guys tomorrow.